Hello students, what's up? How is everyone? Now I think since it's my lecture which is going on, so you must be happy. I don't know whether you were happy or not before my class, but since it's my class, so you have to be happy, right? Okay. So today once again I'm here with you all, and now we are gonna study little more details about the continuous topic which we were doing in the last class. So you do remember, right? I was talking about the cell representation and how to do the cell representation of different varieties of cell, right? Last time we had seen that there was one half cell where H2SO4 was there in the aqueous solution. Then we had this container in order to capture the hydrogen gas which was getting adsorbed onto the surface of platinum, right? So that was one particular type of half cell that we had done. Another half cell was there where I had taken a beaker in which I kept Fe3 plus and Fe2 plus, and then finally we had kept a platinum electrode in it, and I had written the whole cell representation, right? If I'm not wrong, I gave you a question in the last class, right? And the question was something like, what happens when, I remember the question was something. So you have two containers which are given to you. And this time, so earlier on the left hand, in the left hand side container you have ZnSO4 aqueous, and in the right hand side container you were having aqueous solution of Fe3 plus, and you also had the same in the same solution some Fe2 plus ions were present there. There you kept an electrode, but this electrode was an inert electrode of platinum, whereas this electrode was made up of zinc. I connected the two with the help of a wire, and then there was this salt bridge which I had connected, right? So for this particular cell, the representation that you people did was something like zinc in the solid form is getting converted into Zn2 plus aqueous. Then we meet a salt bridge. After that, I said since we were talking about reduction, so first we'll write Fe3 plus in the aqueous state, separated with a comma because the two faces are same only. Fe3 plus is also in the aqueous form and Fe2 plus is also present in the aqueous form. So we write Fe2 plus aqueous. Then there was this platinum electrode. So this was the cell representation of the cell that we had done, right? And then I changed the question a little bit, and I asked you to tell me what should be. Okay, so here let us write the cell reaction also for this particular case. So in this particular case, I said that at anode, since we say oxidation occurs at anode, so zinc gets converted into Zn2 plus in the aqueous state plus 2 electron, right? And in the cathodic compartment, I told you in the last class, so at the cathode we say reduction occurs. So Fe3 plus, which was in the aqueous form, was accepting 1 electron to get converted into Fe2 plus in the aqueous form. Then I said since the number of electrons which are actually getting involved in the reaction should remain same, so since at the anodic terminal you can see 2 electrons are there, so I'll ask you to multiply it with 2 to give you the final equation, which could be written as Zn solid plus 2 Fe3 plus aqueous was gonna give you 2 Fe2 plus aqueous plus Zn2 plus aqueous, right? That was a question that we discussed. And I gave you another question. Let me change it here itself. So instead of taking platinum electrode, I am taking an electrode which is made up of iron only. And instead of taking a solution containing both Fe3 plus and Fe2 plus, we will just have Fe3 plus. Now we need to do the cell representation again. Now see, I didn't change the anodic terminal, so I've kept it like this, whereas when I'm talking about the cathodic terminal, I said after the salt bridge. So that is the salt bridge that we have. And after the salt bridge, we will first meet the Fe3 plus aqueous solution, which is to be separated. Now the iron is there and the iron is available in the form of solid. So this is Fe solid. Right? So my question was that you have to tell me what is the cell representation. So this is the cell representation, this is the cell diagram, and now you have to write the two half reactions taking place at anode and at cathode, and finally you have to tell me the full cell reaction. So this time the cathodic terminal and the overall reaction will get changed. So in the cathodic terminal you can say reduction is taking place. Fe3 plus aqueous will accept 3 electron and become iron solid, right? Then what will I say? I'll say since here 2 electrons are given and here we have a total of 3 electrons, so we need to make it the same number. In maths, you people would have studied something related to HCF and LCM, right? So all those things are to be taken into consideration here also. Multiply the whole equation by 3, multiply the whole equation by 2 in order to make sure that the number of electrons are same. Do not ever do things like here 3 electrons are there, here 2 electrons are there and you are left out with 1 electron. Never. Make sure that the number of electrons should actually get cancelled in both the cases. So you will write we will simply write 3 zinc solid is getting converted into 3 Zn2 plus aqueous plus 6 electrons, and in the other case I will be writing 2 Fe3 plus in the aqueous state plus 6 electrons to form 2 Fe in the solid. 6 electrons are getting cancelled. So when the electrons will get cancelled, the final answer will be 3 zinc in the solid state plus 2 Fe3 plus in the aqueous state is going to form 2 iron in the solid state plus 3 Zn2 plus in the aqueous state, right? So that is the final overall cell reaction that will be taking place if the cathodic terminal will be changed. Okay, so with this, now we are done with the homework which I gave in the last class, right? Now, having done with this particular thing, the next topic that is coming to my mind, which I feel like teaching you people, is something related to what is electromotive force, or what is the EMF of the cell. So that's a question that you need to talk about the electromotive force, or you need to talk about what is the EMF of the cell. Listen to me very, very carefully. If I am asking you to come to this particular electrochemical cell, suppose if I am taking a bulb, now I replace the bulb with the help of a potentiometer. You know, right, what is a potentiometer? So there is an ammeter, there is a voltmeter or a potentiometer. So it is just used to measure the potential difference. You use either a potentiometer or a voltmeter, and these are used to measure the potential difference. To measure the potential difference between the two electrodes. See, you know, right? I am calling this complete system as a spontaneous apparatus. A spontaneous apparatus is something like which will work on its own. You do not need to provide any external source of energy for the functioning of electrochemical cell, right? So if I am saying that it's a spontaneous apparatus, that means no energy is required from outside for the functioning of cell. So you do not need to provide any energy from outside for the functioning of the cell, and in other words you can say the cell will work on its own. Okay. Now see carefully. I told you, right, that electrochemical cell is nothing but it is an apparatus with the help of which electrical energy can be generated. Now you would have seen, right, we use those batteries, the blue colored batteries which are there. They look something like this. Maybe I am not drawing it properly, but this blue color battery we get from market is something like this. Then there are always two terminals which you can see. So one is the positive terminal, one is the negative terminal, right? Or if you look at the cells, so there are the two terminals here, this is positive, this is negative, right? So, and then we have those button cells also. Right? Now we have different varieties of cells. Why do we have different varieties of cells? Because so maybe because this particular is giving me 6 volt, this is giving me just 2 volt or blah blah blah. Like if I want to do some work of a higher energy, I use a battery which is of higher voltage. If something smaller is to be done, then we use a cell with a smaller voltage, right? That means the most important thing that is coming here is the potential difference between the two electrodes. And the potential difference between the two electrodes in our daily life we call it voltage. What is the power of the cell? What is the voltage of the cell, right? And this we are gonna study now. That means if I am taking a particular anodic compartment and I am taking a particular cathodic compartment, and now I am keeping a potentiometer or a voltmeter here. So the voltmeter or the potentiometer will not always give the same value. Some cells will be of a higher voltage or a higher potential difference, whereas other cells will be of lower voltage or lower potential difference, right? So now to define the potential difference, we will say a new term which is electromotive force. So let's try to study the details of electromotive force. The electromotive force or the EMF of a cell is defined as, so the electromotive force or the EMF of the cell is defined as the potential difference between the two electrodes. So the the electromotive force or the EMF of the cell is basically defined as what is the potential difference between two electrodes. The definition is not complete. You need to add on another few points when no current is being drawn from the cell. This line is really very important. Look at the board carefully. I am saying suppose there is a gap in the circuit. Okay, the circuit is having a gap. Gap means the circuit is not complete. You do agree, right? Whenever I am putting an iron electrode into the Fe3 plus solution, a potential difference will be generated. I told you, right, that kuch hota hai story that we did. That means something will happen. And what was that something? There was this potential difference, right? There was this electrode potential which will be there in the right hand side compartment. Okay? Let us say there was a potential difference of 0.8 volt. Fine. And now I am saying when zinc electrode is separately kept in ZnSO4 solution, then also kuch hota hai, right? Then also something will happen. And let us say here the potential difference was just 0.2 volt. Okay. Now instead of considering that a zinc electrode, when it is dipped in ZnSO4 solution, a potential difference of 0.2 volt is there, right? And here when iron electrode is kept in Fe3 plus solution, again let us say there is a potential difference of 0.8 volt, right? Now don't you think there is a potential difference in both the two containers? So the right hand side container is at a potential of 0.8 volt and the left hand side container is at a potential of 0.2 volt. Now when both are there, but we didn't connect them. So this side there is a potential of 0.8 volt. This side there is a potential of 0.2 volt, right? So don't you think if I am connecting a bulb over here, so if a bulb is connected over here, the bulb will be getting a potential difference of potential of 0.6 volts, right? This is what is potential difference. So we say that the electromotive force or the EMF of a cell is basically defined as the potential difference between the two electrodes, but when no current is flowing from the cell or when no current is drawn from the cell. Right now I didn't connect them, there was no connection between the two, and this is what is a maximum potential difference you could have measured as 0.6 volt. And this potential difference is also known as EMF of the cell. Okay. Now let me, since I have explained you, let me just write down everything in detail so that it is easy for you people to understand and it is easy for you people to remember also. So let me start writing. The two half cells, that is the anodic compartment and the two half cells, that is the anodic compartment and the cathodic compartment. Are having their own potential, are having their own electrode potentials. right? So when I'm talking about anode, since zinc or any particular metal electrode is dipped into the metal solution, so there was a potential difference that was created within the anodic compartment. Similarly, when another metal electrode is dipped in metal solution in the cathodic terminal, there will be a potential difference that will be generated in the cathodic compartment. So I am saying that the two half cells, that is the anodic compartment and the cathodic compartment that are there, they are having their own electrode potentials, right? So these are known as the anode potential and the cathode potential respectively. Okay, so these are known as the anode potential and the cathode potential respectively. So when the anode and the cathode are not connected to each other, let me write it down. When the anode and the cathode are not connected to each other, but they are placed close to each other, By the way, this definition or this line that I have written for you people is just for so that your concepts can be cleared. See, if I am saying in the anode, the anodic potential will exist, in the cathode, cathodic potential will exist, they will not exist individually. You agree, right? Because when I am taking ZnSO4 and I am putting zinc in it, I told you that zinc will keep on losing its electron, so that a potential difference should be developed. So it will lose its electron till the point a potential difference will be developed, right? But that potential difference will be developed if and only if you are connecting it to the cathodic compartment as well, because we need the flow of electrons. If there is no flow of electrons taking place, you can't talk about them individually, right? So I am saying when the anode and cathode are not connected to each other but they are placed close to each other. What do I mean by this statement? I am saying that yes, you have connected them with wires, but then you didn't connect the two wires. Okay, you are just trying to measure the potential difference. So when the anode and cathode are not connected to each other but they are just placed close to each other, then a potential difference will exist between the two compartments as well. So I am saying when they are not connected to each other but they are placed very close to each other, then also there will be a value of potential difference that will exist between the two compartments as well, right? This value of potential difference, so obtained when no current is drawn from the cell. When no current is drawn from the cell. Is called the EMF of the cell or the electromotive force of the cell. Okay, so I am just defining as of now that the potential difference value which occurs when the two compartments are not connected to each other, when no current is drawn from the cell, that particular potential difference is called the EMF of the cell. Okay. So now first you have to note it down so that then I can finally tell you why did I give the statement that no current has to be drawn from the cell. What happens if I start drawing current from the cell? Okay. So now I'll give you the answer, but before that note it down so that I can clear the board for you people. Okay, so I think everyone would have written down the definition of what is EMF or electromotive force of the cell. Now there is this question that why do we define the EMF of the cell when no current is drawn from the cell? So let me try to give you an answer to that particular question also. See, you know, right, there is something related to the resistance provided to the flow of current. So when the electrons try to flow from one position to the other, or when the ions try to flow from one position to another, there will be some resistance which will be provided to the flow of current. So if I am saying that this is the container, these are the two containers in which some electrolytic solution is kept. You are immersing two different electrodes in the container and you are keeping a salt bridge. And now here you are trying to measure the value of potential difference, right? Since the two half cells I am saying are different, maybe this is zinc, ZnSO4, and maybe this is copper and CuSO4. Okay, so you need to make sure that the two half cells that you are using are different. Fine. Now see carefully. Let us say when there was no current which was being drawn from the cell, the concentration of the solution also matters here. So you have taken one particular solution here. So let us say there were 100 Zn2 plus and 100 SO4 minus, and we had zinc here. Similarly, we had copper here. And we have taken 100 Cu2 plus and 100 SO4 minus, right? That means now when zinc is being dipped in the ZnSO4 solution, there was a potential, and let us say the potential in the left hand side compartment was 0.2 volt. It's not 0.2 volt actually, I am just taking it as a reference, okay? Similarly, the potential in the right hand side compartment when copper was there and 100 CuSO4 molecules was there, so it was 0.8 volt. Okay. Now I am saying you measure the potential difference, it will give you 0.8 minus 0.2. This is 0.6 volt, which you said is the EMF of cell. Okay. So let us say you are getting a battery or a cell from market, and the cell is always sealed, right? It's completely sealed. We always check whether the cell is not used. That means, and over it is written 0.6 volt. That means this is fresh. When you start using it, the very first time you measure the potential difference, the value of potential difference will be 0.6 volts, right? However, when I say connect the two with the help of a switch, connect them, make the circuit complete. So what will happen? Electrons will start flowing. Now you know, right, when electrons flow through wire also, wire offers some resistance, right? Now the electrons will get accumulated, so they will flow through the copper electrode. Some iron thing is taking place here, copper 2 plus will be there, blah blah blah. So more of SO4 2 minus will be developed here. Then there will be the maintenance of potential difference, as well as there will be the maintenance of complete circuit through the salt bridge, where also you will see some resistance. Now as soon as we say that Zn2 plus will be here, so one Zn2 plus to flow from one position to the another position will also feel some resistance. That means and then electrons will come here. Now these electrons will start moving. That means throughout the path where either the electrons are moving or the ions are moving, throughout the circuit resistance will be offered to the flow of current. Now flow of current, because there can be flow of electrons also, as well as there will be flow of ions also. Okay. So now slowly and steadily, if you try to measure the potential difference, the value of potential difference will be little lesser compared to what you started. And that is the reason, right, when you buy a cell from market, like let's say it's a new cell, you are buying it from market and it says I'm 0.6 volt. So it will work as if it is 0.6 volt actually. You use this cell for 1 month, for 2 months, 3 months, 6 months, 1 year. After 1 year, it's like you would have seen, right, the wall clock which are there. So if you put the cell, they'll be functioning very nicely. And then after a few years, or let's say after a few months, when the cell starts getting degraded, so first the time will be fluctuating in the watch, and then one day the watch will stop working. Why the watch stops working? Because the potential difference which was there in the cell was getting reduced, and one day it came to 0 volt and we said that the cell is dead. Right? So we always say that when you are measuring the EMF or when you measure the electromotive force of the cell, you always have to measure it when the two electrode terminals are not connected to each other, when the current is not withdrawn from the cell. Once the current starts withdrawing, like once the current starts moving in the cell, or once the electrons will be migrating from one position to the another, they will be facing some resistance. Because of the resistance faced by the movement of electrons, so because of the resistance which will be faced by the electrons, the voltage drops, and thus you won't be able to tell the exact value of the potential difference. Okay, so this is the reason why we say that the electromotive force is measured when no current is drawn from the cell. Fine. Now see, listen to me for 1 more minute. When we are talking about the two half cells, we say that in the left hand side compartment, oxidation occurs. Right? So the potential that I will be measuring will be oxidation potential. Now what do we mean by this term oxidation potential, or what is this electrode potential? Now let me go into the details once again. So electrode potential, I am saying, as the metal electrode will be dipped as the metal electrode will be dipped into an aqueous solution, of its ions. As the metal electrode will be dipped into an aqueous solution of the ions, the metal atom from the electrode will start getting oxidized, right? The cationic part will go, will continuously go into the solution and the electrons will, and since the electrons cannot flow through the solution, and since the electrons cannot flow through the solution. Why the electrons can't flow through the solution? Because of the resistance provided by the solution. Because of the resistance provided by the solution. So I am saying, since the electrons cannot flow through the solution, the electrons get accumulated, the electrons start getting accumulated on the surface of electrode. On the surface of the right? This process will keep on, so the process will continue. The process will continue till a saturation limit is achieved. Till a saturation limit is achieved. Okay, so this saturation potential will be called as the electrode potential. Will be called as the electrode potential. Right? That means if I am talking about that zinc is continuously getting converted into Zn2 plus going into the solution will start getting positive charge, right? And since the electrons are getting accumulated onto the surface of electrode, so the electrode gets a negative charge. The process will keep on going till a point where saturation is achieved and no more zinc atom wants to be converted to Zn2 plus, right? So we say that there is a potential difference in this particular compartment. But for this compartment, since you are talking about the oxidation, so this is known as oxidation potential. However, when you are talking about this compartment, for this compartment I am talking about reduction potential, right? That means whenever you have any couple Zn, Zn2 plus Cu, Cu2 plus Fe, Fe3 plus or Fe, Fe2 plus or anything, it has got both the tendency to get oxidized or it has got both the tendency to reduced, right? But it depends upon which two you are taking. The one which wants to get oxidized will get oxidized, the one comparatively which doesn't want to get oxidized will get reduced. So this brings me to another topic, which is the electrochemical series, which simply says which has more tendency to get oxidized and which has more tendency to get reduced. Okay, the lecture is still not complete. It has got something more to be taught to you, but then I think you are actually saturated watching this thing because it's little confusing. Okay, so I am trying my best to go slow so that you can understand each and every single point very nicely. In the next class, we will move on to the topic how to measure the individual potential and then how to find the actual EMF of the cell. By this time, you have already understood what is the EMF of the cell, but how to calculate it, this I'll tell you in the next class. So make sure if you want to understand the next class, you need to literally revise what we did in today's lecture. This is really important, okay? So with this note, I would like to take a leave. I'll meet you once again in the next class. Take care. Bye-bye.